and welcome to the Building Sociology Potty, where we talk about better buildings to live and breathe in. My name is Jess Kismet, and today I am joined by Dr. Cameron Munro. Cameron is a building scientist and the founder of Passive Analytics, which is a consultancy based here in Melbourne, where we are currently, that helps designers, builders and homeowners understand how buildings truly perform. Cam has a background in engineering and a deep passion for making homes more comfortable, durable and energy efficient. He is one of the best minds in our industry. His understanding of building performance is second to none, and he's an incredibly articulate communicator as well, which means we can all easily benefit from his knowledge. And I'm really looking forward to this chat. Cameron was also recently a guest on the Mindful Builder podcast, and the conversation was excellent. So if you haven't heard these episodes, I recommend you go back and have a listen in conjunction with this conversation. I'll link them in the show notes as well, or you can just look up Mindful Builder on your favourite podcasting platform. I'm going to try and build on that conversation today. So without further ado, I would like to welcome you to the Building Sociology Potty, Cameron.
Thanks very much, Jess. Good to be here.
Excellent. So let's get to know you a little bit. Let's have a little bit of a chat about your professional history and how you got to where you are today.
Sure. Okay. So I did aerospace engineering here in Melbourne as an undergrad. And then from there moved to Sweden for about 6 odd years to do my PhD, also in aerospace engineering. And then over to the UK for a few years before ultimately making my way back to Australia. And we've had a couple of different careers over that time. But all of them have been around the idea of modelling, numerically modelling of different things, be that aircraft, transport systems and now buildings. And so I guess the way I approach the world is very much about following the numbers rather than guessing. And when it comes to buildings, that's particularly true. When we're trying to make decisions, for example, as to how much insulation we should have in a building, whether we should double glaze or triple glaze our windows, we can model all of that. We can assign numbers to it and therefore run trade-offs as to what the best combination is going to be for a particular building in a particular climate.
It makes sense. Do you have much to say on the translation of those numbers to reality?
Well, yeah, that's always the hard bit, isn't it? So it's trying to communicate to clients and to builders and indeed architects, building designers as well, those trade-offs in a way that actually allows them to make actionable insights. You know, it's often what we talk about in engineering or certainly in modelling is you don't want to just do the modelling as an outcome in itself. It's got to actually provide insight for, say, the homeowner client to actually make an informed decision as to say, okay, if I do that, that's going to far more cost effectively improve the thermal performance of my building than if I do that over there. And so to provide some numbers around that to allow them to make informed decisions rather than simply relying upon guesswork or expert judgment, as it were, from the builder, architect or someone else as to what they ought to do.
So it's about understanding and communicating the why behind how decisions are made.
Often, yeah.
Yeah. And I understand we are currently in Cameron's home in Melbourne. And when we walked in the front door, straight away, the house felt warm. It's about 12 degrees, 14 degrees outside.
That's Melbourne in winter.
Today.
Something like that.
Yeah, it's cloudy outside. And as soon as we walked in, the first thing I said was I didn't know that there'd been renovations done here. And I thought, it's warm in here. So could you tell us a little bit about what you've done to this home to make it so comfortable?
Yeah, okay. So it's a weatherboard home, so your classic Australian weatherboard. So it was a leaky sieve. It happened to have a 1980s extension on the back that was, pretty poorly built. Didn't look great either. So the extension out the back was completely demoed. The weatherboard at the front, we're subject to a heritage overlay here, which means we can't destroy or knock down the front of the house, but we gutted it internally. So I took it back to frame, essentially, and then re-insulated it, added a membrane for air tightness and vapor control internally, put in a HRV for ventilation, so mechanical ventilation, and the level of insulation is roughly twice that would be required by building code around here.
So R4?
In the walls is essentially R4. Yep. The build-up's a little different. And then, R6 plus in the ceiling. I mean, the advantage of ceilings, especially in our case at the front, we've got a pitched roof, is you've got buckets of space. So if you've got insulation left over, you throw it up there. we ultimately, this was about a decade ago that we did this project. I was trying to hit certification, so NFIT for Passivhaus aficionados out there, and be one of what would have then been, I think, the second or third in the country.
10 years ago.
But it was hard work, and we got down to 1.2 ACH on the air tightness. So for Passivhaus, for NFIT, you've got to hit 1 ACH.
Just missed out.
We didn't quite get there. We did 4 rounds of blower door testing, and at the time I was bitter and twisted about it. But ultimately, you've got to move in.
Yep.
And you've got to get on with your life. And of course, the reality is that the difference in terms of energy and comfort between 1.2 and 1 is completely negligible.
Yeah.
It really doesn't matter. So we need to be pragmatic as well as obsessed.
Yeah, absolutely. Under construction, renovation projects or retrofit projects can be really hard with membranes and just upgrading the building fabric in general. So have you got any boundary walls or issues here with membrane install, or did you just do the internal Intello membrane?
Yeah, so in the extension we did, the new extension, obviously you've got a clean slate, so you can do internal and external. We were debating what to do at the front with the weatherboards.
Yeah.
So we had old hardwood weatherboards. They're generally speaking in decent nick.
Yeah.
And so, in theory, the best thing to do is to pop them off and put an external membrane and then a ventilated cavity batten in. We just chose not to do that, which is, potentially risky. But again, it just came back to that compromise between cost, time, and respecting the heritage of the building. And if you've got an old timber weatherboard, often replacing it with a new softwood weatherboard, you're really going to get that long-term durability of that. But probably the trickiest detail in this building was the rammed earth wall that's behind us now. Of actually trying to tape the internal membrane to the top of that rammed earth, because it is inherently quite a rough surface, and trying to get that adhesion right with the glue, and also a line of tape hidden away under the ceiling was a challenge.
So taping the internal membrane here on just behind us,
and also at the ceiling plane. So I've got a rafter ceiling above us, and then we've got a suspended ceiling, of course. But we're trying to run our membrane around onto the face of the Intello and then tape and seal it. So it felt like it was death by, as is always the case with air tightness, it's death by 1,000 cuts. There's never one panacea when you go around and go, there's my solution. That's my money win. It gets to a point when you're sort of down in that one sort of ACH range that you've got probably 50 tiny little leaks that are very difficult to find. And at some point you just have to say, near enough is good enough.
Okay, well, job well done here, Cameron, because this house is incredibly warm. And have you got any active heating and cooling on at the moment?
No, not at the moment.
I think it must be, by feel, I reckon it's over 20 degrees in here, easily 24, 25 degrees in here right now, would you say?
It wouldn't be quite that warm, but
feels it to me.
20 to 21 probably compared to where we've been outside. That's probably the difference. But we've just got 2 single split ACs, one in the front, one in the back half of the house. And perhaps there's a learning there too, is when we did this, obviously we were rather early in the Passivhaus movement as it is in Australia. We only installed the single AC in the back half of the house in the living room where we are now, under the assumption that the HRV was going to move that heat and coolth in the summer from the back to the bedrooms at the front. And that's not quite how it works, because the HRV is moving air at a relatively low rate. And so it really doesn't act to redistribute your heat through the building. So if you are building a high-performance building and you are going down the split system route, as many of us would do, you really need to consider having multiple splits through your house to try and distribute that heating and cooling. Otherwise, what you'll get is a well-conditioned section of the house, but the HRV just won't move that heat to the other half. Now, having said that, being a high-performance envelope, it's only 18 degrees on the cool side in the other half of the house if you don't have the heating on. It's not 10 degrees as it would have been in this building initially. But having gone to the effort, 18 degrees is not going to meet your comfort expectations, certainly not ours. And so we installed a second AC in the front of the house later in order to get that distribution of heating right. And so what I often do in my projects now is I'll usually install 2 splits, or recommend 2 splits to be installed, and possibly even rough in for a third and just leave the
Yeah.
pipework in the wall so that their client can come back later and install one if they so wish.
That's really interesting. It's a really interesting point because, I mean, Passivhaus markets itself on, no heating and cooling. Um, and in some parts of the year that can be true. But I think that having the ability to actively heat and cool your spaces is still really important as
Yeah.
humans.
And I think we have to be really careful, don't we, in the passive house space. I think, the phrase passive does indeed suggest no heating and cooling,
Yeah.
but that's not correct.
No.
The modeling is always about there's a heating demand and a cooling demand. There's an amount of energy you're going to require to maintain a minimum of 20 in winter and a maximum of 25 in summer. And so you still need active heating and cooling.
Yes.
We cannot get away from that. And we need to reiterate to our clients, I think, to say, look, we need that heating and cooling system. You are going to need to operate it in the middle of winter. So now, mid-June in a dreary, cold, miserable Melbourne, if you're in a passive house, you will need to turn your heating on.
Yeah.
That doesn't mean there's a problem in your building.
No.
It's just that's how it's designed. But that system is then going to run at a relatively low load. So you'll need very significantly less energy to maintain that 20 degrees than you would otherwise have done. But it's not zero.
No, it's not zero. And equally in summer, there's with highly insulated, airtight buildings, there's overheating issues in Australia. So, if you have a room on the west facade, for example, that has no active cooling in it, that room could overheat if it's not shaded correctly or adequately, et cetera, et cetera. So there's definitely still elements of a passive house building that need to be actively heated and cooled and controlled.
Yeah, that's true. I would sort of be cautious about a correlation between a high-performance building envelope and increasing the overheating risk, because insulation, of course, works just as well, whether it's hot inside and cold outside or hot outside and cold inside, and reducing that thermal transmittance. The issue probably becomes that if it does cool down overnight in summer, so say it was 35 during the day and drops to 15 overnight, in a conventional poorly insulated building, that heat that's built up within the house during the day can then dissipate out at night. Whereas in a high-performance envelope, that's no longer the case. You're retaining that heat. And so you need a way of purging it. And that's where being an active occupant, opening your windows when it does cool down makes sense. But during the day, the critical thing is always the glazing.
Yeah, that's what I was going to say. Yeah.
And it's always external shading. We're talking about high-performance glazing units, an internal blind with a pelmet and whatever. That works with single glazing. That does not work with your very high-performance glass. So then you have to push your shading strategy to the outside, be that a deep eave, be that a blind, deciduous vine, any number of solutions.
And this is where the modelling comes in to help you make those decisions.
Absolutely. And this is what I would do in every project is I model each and every window and I'll say, what if there's a blind on this one? What if there's a blind on that one? And then I'll rank them and say, here's the sequence from 1 to 10 of all of your windows. Number 1 is the window that you need to put a blind on first, and then you just work your way down as far as budget and your comfort expectations match. So some clients will say, I never wanted to get above 23 in my house, in which case you need to push for more blinds. Others will be quite comfortable at 27, in which case you might need fewer blinds.
Yep. Interesting. Very interesting point. So as we're talking about HRV, let's actually touch on that before we move on. This point at which mechanical ventilation is required. 5 ACH is in the building code. Please discuss.
So this is great. So I think there's a lot of misunderstanding about HRV, and I think we've got to sort of split it out into its two components. So there's a V, there's a ventilation bit, and there's a HR, heat recovery bit, or MVHR, same thing, the mechanical ventilation and heat recovery. The primary purpose why we're doing this is for ventilation, fresh air into our building. The V, that's the bit that's critical. Each and every building needs mechanical ventilation, full stop, no argument. I don't care what the air tightness is. Every building needs mechanical ventilation. Why is that so? Because even if you have a very air leaky house, like the house that we were in now, prior to the renovation, was probably wouldn't have got to 50 pascals of pressure. It was well north of 30 ACH, a leaky sieve, your classic Australian house. And when it was windy outside, you would have had heaps of ventilation through the house, far more than you would need or want in terms of maintaining a comfortable indoor environment, but more than adequate for ventilation purposes. But the majority of the time, it's not that windy, certainly not here in Melbourne. And there might not be a big temperature difference in to out. And so you would not have anywhere near an adequate level of fresh air coming into the building. There's simply no control. You're relying on poor building practice to provide adequate air supply, or you're relying on the occupants to open a window. Well, how do you know whether you've opened the window far enough? If you go to bed when it's windy, you just need to crack the window open. If the wind dies down overnight, then you should be getting up at 2 a.m. and opening it further. But you have no way of knowing how much airflow you're getting in. Whereas the mechanical ventilation is providing that controlled, continuous, regulated, filtered flow of fresh air, regardless of what the outdoor environment is doing. Then you come to the second point, which is the heat recovery. So the easiest way to do mechanical ventilation, just step back a second, is simply to turn on your bathroom extract fans and leave them running 24/7. That will give you fresh air into your building. But, of course, that's not going to work very well for you in the depths of winter or the height of summer, because you're dragging in that warm or cold air from outside, which you don't want to be doing.
It's also noisy.
And it's very noisy.
Very overload.
Yeah, and it's not actually necessarily ventilating all rooms in the house, depending on the airflow pathways. So there's a bunch of other reasons why that's generally a bad idea. But it comes to the point of how you need the heat recovery, because you want to take out that stale, moist air from the building, but in winter at least, you want to retain the heat and re-inject that into the incoming air, and hence the heat recovery. And this is where the relationship to the building envelope air tightness comes in. Because if you want to have a really high heat recovery efficiency, it's a function both of the heat recovery efficiency within the HRV itself, within the core of the unit, and also of the building envelope itself. Because if you're only extracting 40% of the volume of air through the HRV and the other 60% is escaping through the building envelope, you're not recovering any heat from that 60% escaping. So you want to try and build a nice tight envelope, so you're forcing all of that extracted air through the HRV such that you've got a chance to recover the heat. And that's where the relationship to air tightness comes in. So to make the HRV work most efficiently, you want to be as airtight as practicable. But for ventilation, for fresh air reasons, the air tightness is essentially irrelevant.
Yeah, yep. So to repeat back to you what you said, the HRV is for fresh air regardless of air tightness score, and the heat recovery is to make the air tightness and heat recovery portion are to allow that system to operate at its most efficient level.
Correct, particularly given that your HRV is going to cost you very significantly more than just putting a couple of fans in your wall or your ceiling. You want to actually utilize that asset to its best value, which really pushes you towards going to a fairly airtight level.
And if you have a less airtight building envelope, this is a question that's popped into my mind. If you have a less airtight envelope, that system has to work harder in order to move air, or the same volume of air through its system. Does that mean that the system is then louder? Talking about the noise of an HRV system?
Shouldn't really have to work any harder, because it's still moving the same volume of air.
Okay.
So you've calibrated, you've set the system up to extract, say, 150 cubic meters of air an hour. So the fan is spinning in order to do that. So yeah, it shouldn't really play a significant role. Probably the other part to this equation, though, comes to moisture management, because what HRV is also doing, of course, is continuously extracting moist air from your wet spaces, which is absolutely critical. Your first line of control, defense to stop moisture vapor getting into your wall, getting into your ceiling space, and risking getting condensation, is to get rid of it in a controlled way. And the HRV is doing that 24/7. And then in combination, you're trying to make an airtight envelope to prevent any of that vapor that should happen not to be extracted through the HRV to get into the wall and thence condense.
And in terms of extraction fans, something that I think doesn't, it sort of when I learnt this, it surprised me, but of course it makes sense. If you have an airtight building envelope and only extraction in your wet areas and no supply air, then those extraction fans, depending on the level of air tightness that you have achieved, they don't work as efficiently because there's no makeup air, to use an engineering term. There's no air coming into the building to allow air to be extracted from the building.
Yeah.
So this is a really important consideration, I think. If you're getting down to, let's pick a number, 2 or 3 air changes an hour, and you put in a standard extraction fan in your bathrooms, you may find that it's not at all working the way it should be.
And that's right. And the other obvious one is a range hood.
Yes.
In your kitchen. So if you build to a fairly airtight level, you switch on the range hood, and when you look at the data sheet for the range hood, it'll tell you, 600 cubic meters an hour or something of that order, perhaps. And that's often with a certain duct length, and you've got an extract duct with an elbow in it and might be 5 meters long, so you've got a stake pressure drop there as well, so it's declining. But yes, the system has got to be in balance. If you extract air from the building, at some point it's going to depressurize to a level where all the walls and the roof cave in. And that's clearly not going to happen. We're not going to create that level of a pressure differential. And instead, there will be air leaking in. And in an air leaky building, not a problem. Air will just leak in everywhere and everything will operate fine and dandy, as it were. It affects comfort, though, of course. But in an airtight envelope, you need a make-up air solution. Now, in very airtight buildings like passive houses, if you've got a very powerful range hood, it can often produce enough static pressure to actually still extract adequately, because you're never 100% airtight. But if you have a fairly modest range hood, then you might well find at some point you get to a level where the fan just spins and not much air moves, which is defeating the purpose, whether it's an extraction fan in a bathroom or a range hood in a kitchen. So often you will need a make-up air strategy. And what we've been pointing to in Passive House lately is sort of things have moved very much, I think, now towards externally venting range hoods. We used to be on internal recirculation and carbon filtration. I think for air quality, it's right that we should be pushing to the external solution, but it is much more difficult because you've got to make the external vent airtight, and then you need a make-up air strategy, which can be done in a complicated way with another make-up air duct and a fan, and can all be electrically linked, or you can simply open a window.
Well, that's, crack a window, which then compromises all of your energy efficiency.
But so does a make-up air duct through somewhere else. I mean, the reality is with a range hood in particular, you're looking at extracting very high volumes of air, 3 or 4 times that of what your HRV is doing an hour. And so you're going to need to provide a supply make-up air solution. And if you put it relatively, the balance you're trying to achieve is you want it close enough to the range hood that it doesn't entrain warm air from the other end of the house and create this draft down your hallway, down to the kitchen and out. But you don't want to be so close to the range hood that you don't fully capture all of the pollutants that are coming off the cooktop. And so you want to be, for argument's sake, a couple of meters away to allow that incoming air from that window, or whatever it may be, to come to entrain all the pollutants coming up from the cooktop and then out the range hood without creating too much draft.
And that is why a mechanical HRV system, the word balanced mechanical HRV is key, because it's an equal supply as extract. And there's no need for cracking windows or extra vents and things like that.
And that's the great thing with HRV, isn't it? That there's nothing really for the operator to do. And in fact, time and time again, we get problems with HRV installs because the client has actually gone and meddled with it. and instead, the message I think should be in our when we do a handover to our clients, don't stuff around them.
Set and forget.
Set and forget. Every 6 months, it'll beep at you and tell you to change its filters. That's all you should do. We've set it up such that it'll just tick away now for many years to come, as long as you don't go fiddling with it.
What do they typically fiddle with?
There's also set it on summer bypass or something that someone told me this morning. There's all sorts of ways to it. I mean, humans are great, aren't we? We're very good at taking things that are working fine and breaking them.
Indeed. All right. So let's move on to something a little bit different here. Let's talk about moisture and water ingress. As you know, you've taken your home here from an older, 30 ACH older home, and you've improved it out of sight to make it more comfortable. over and above the building code, but there are also renovations being done to make homes just more comfortable in accordance with the building code. And as you've got an HRV system in this home, which a lot of homes who are having improvements done to them won't have. So as we are creating warmer, more humid environments inside, more airtight environments, we are creating condensation risk. And so now we're not only getting moisture ingress from driving rain and cladding leaks, we're also getting moisture occurring in our buildings from inside. So how can we explain vapor diffusion and condensation risks to builders in a way that makes sense to them?
Okay, so it's a tricky one, isn't it? So I think the first thing to say is the water vapor is all around us, always, wherever we are in the world. It will vary the quantity of that water, and then so you can't escape the presence of the vapor. But what we're wanting to do is stop condensation. We're wanting to stop that vapor from actually condensing. And so there are two ingredients to this equation. There's vapor and a condensing surface, which is a fancy word for a cold surface. And so you get that beer or that bottle out of the fridge, like now, I can't see water vapor in there, but as soon as I get that bottle out of the fridge, I know it's going to get condensation on the surface. What's changed? I've got a condensing surface, a cold surface for which the vapor can condense onto. So if you can get rid of the condensing surface, you don't have a problem. If you can reduce the vapor below the dew point, which is a fancy term for how much water can be sustained within an air mass at a certain temperature, you don't have a problem. So heat your air so that it can support more
moisture.
vapor, more moisture, and remove the condensing surface by insulating or making sure the layers in your building envelope are such that you're not going to get condensation on those surfaces.
So let's take a steel frame building, for example. One giant condensing surface in the wrong conditions. So how would you stop that condensation from happening on a steel frame building?
So your classic way of doing a steel frame stud construction, of course, is you insulate between the studs, just as you do with timber frame construction. And then, of course, all of your studs are cold in the winter. And so on the back face of your plasterboard, you're just creating these lines of cold surfaces on which the condensation can form. So the only way to solve that problem is to warm the steel. And to warm the steel, you have to externally insulate. So and this is where we get towards this notion of the perfect wall, is that you have exterior insulation. So you separate out your structural layer, a steel frame in this case, and you put the insulation, maybe it's a foam cladding, whatever it may be, on the outside face of that steel. So now in winter, and we're assuming here like a Melbourne, Adelaide, Hobart, whatever type climate, that as you condition the inside of the house, the steel frame heats up to exactly the same temperature as the room temperature, so say 20 degrees. And at 20 degrees, you're very unlikely to get condensation on that steel unless you have an awful lot of moisture in your house.
You made a really good analogy in the Mindful Builder podcast of the conductivity of different materials. Could you just repeat that quickly so that the listener can understand how conductive steel is?
Yeah, okay. So you've got three ways of heat transferring. You've got conduction, convection, and radiation. Conduction occurs in solid materials. So in a solid, you've got a bunch of atoms joined in a lattice. And what's heat? Heat is energy, kinetic energy. And so those atoms vibrate and they tap into the one next door and they transfer heat. That's conduction. And so conduction occurs in solid materials. And so you have very low conduction in some materials like your foams, plastics, and so on, up to very high conduction in things like steel and even more so aluminium. But you get big differences even between metals. So something like a carbon steel is about 30 watts per meter Kelvin. So this is the measure we use for thermal conductivity. A lower number is better. So just to give that a scale, your typical glass wool insulation batt is maybe 0.04. So you're at 30 with carbon steel. So divide those through, that's many hundreds of times more conductive. Then you've got other steels that are up around 50. So you've got a big difference there. And then your aluminium's up around 250. So what's the worst material we could use to build our window frames from?
Definitely aluminium.
Aluminium. And why do we get condensation on aluminium window frames in the winter? Because they're a condensing surface. And so if you want to avoid condensation, which we all should, we should not be accepting this idea, this culturally embedded idea in Australia that, oh, it's winter, I get condensation on my window.
Mm.
No, that is not acceptable. That is not just how it is. We can do better than that, and we know exactly why it's occurring.
And we know how to fix it.
And we know how to fix it.
Mm-hmm. Indeed. What I was also getting at was the analogy you made between, you've got a fire and you stick a piece of timber in it, or you stick a piece of steel in it, or you stick a piece of insulation in it, and how quickly the end that you're holding gets hot. So yeah, I thought that was a really good visual or practical example of thermal conductivity. Do you know what the conductivity of copper is off the top of your head?
No, I don't.
No, I've been meaning to find out. It's time for a quick sponsor shout out. Today's episode of the Building Sciology Potty is proudly brought to you by our amazing sponsors, Enduro Builders and Climasure. A huge thank you to these incredible businesses for supporting the podcast and helping us spread the word about better buildings to live and breathe in. Your support makes this podcast possible. Please head over to their websites and follow their social pages.
Objective here again is to eliminate condensing surfaces, and so your primary objective with any steel in your construction is to keep it on the warm side, so towards the interior. So the classic, to pick a profile, say you've got a PFC lintel above a sliding door somewhere, might have a 90 mil deep flange on it. So you'll often then have to push that wall out to 140, say, timber framing to give you 50 millimeters of space towards the outside face of that PFC, so that you would run something like XPS and polystyrene insulation to try and keep the steel on the warm side of your assembly.
And it's something that needs to be detailed during design, and because if you give a builder a detail with insulated steel and they've never seen it before, or you surprise them with it, or they'll say, oh, I've never done this before, and that's not how we do it, and blah blah blah. So those conversations about using the XPS or EPS insulation on the outside of a steel frame, all of that collaboration and communication needs to happen very early on.
Yeah, you'd really need to see that in the section details in your drawing set. And then the other tricky bit that comes in with steel often is obviously you're often carrying that load into a column, like a steel SHS column. So you, again, assuming it's 90 mil square, you'd externally insulate it, but then it's going to have a bottom plate. It's going to be sitting on, say, a cold slab, or if it's a suspended timber floor, it's going to be penetrating through the thermal envelope to the subfloor. And so you've got to come up with a detail for that. And so best practice would be to, with say, the slab connection, is to put a structural thermal break material underneath. But of course, that's got to be signed off by the structural engineer too. Yeah. So all of that has to be detailed prior to construction. And of course, all these shop drawings have to be done to account for those different dimensions that might change.
Absolutely. Great advice. If you, in your experience, where do most insulation installs fall down? Is it gaps, compression, wrong product selection, or something else?
I'd probably go with 1 and 3. So, gaps and wrong products, not so much wrong product selection, but wrong product sequencing. So start with the gaps first. So you only need 5% gaps, very tiny gaps. So imagine you've got a wall and you put your insulation between your studs that are fairly nice and tucked in neatly, and then it drops down below the noggin, and maybe you're saving some money and going for a fairly lightweight, soft and fluffy wall bat, and invariably that's going to sag over time. And as soon as it starts to sag, those tiny little gaps will have a very disproportionate effect. And
how do we work that out? Because there's these sort of, sorry to interrupt you, Cameron, but there's a lot of information, a lot of statements around how tiny gaps will decrease your insulation performance by 40%. Where do those numbers come from?
So the best way to do it is in a hot box. So you take a sample of the wall and you heat one side of it, and then you can measure the heat flow across to the other side. Just do it experimentally. That's one way. But you can also do it theoretically too. So you can do it in the thermal bridge calculation. There's the fancy term is a finite element analysis. So you take a detail and you break it up into a whole lot of tiny little squares, and you run a bunch of equations on that to allow heat flow to move through that that build up
Right.
that you've got, and you can assess the impact.
Mm-hmm.
But probably the more difficult part of it, so you've got a conduction problem, but you've also got a convection problem, because air will be moving through that gap too. And when the air moves, it's taking heat with it, and even more problematic, it's taking vapor with it. And if it takes vapor with it and moves from warm to cold, boom, we've got potential condensation problems.
Yeah, and that's the cold spots. The cold spots equals mold spots problem when you have gaps in your insulation.
That's right. Yeah. So that's the problem with gaps. You've just got to be super diligent about the way in which you install it. I'm not so fussed about compression. Mild levels of compression within your fibrous insulations, like your glass wool, is not a big deal. 5 to 10%. Okay. Obviously, if you go to the other extreme and just compress a glass wool bat that was supposed to be 90 mil down to 20 or 30 mil, then you've lost all your benefit, because the whole reason for that bat's existence is to create lots and lots of air pockets. That's what insulation is, lots and lots of still air gaps. If you eliminate those air gaps, well, you've just got glass now, which is not going to get you very far. But to your third point about wrong product selection, it's more about the layering, I think. And this is where you say, for example, say I've got a 90 mil timber frame and I put an R2.5 glass wool bat in there, which is pretty standard in southern parts of Australia. And you go, well, I'd really love some extra insulation here. Why don't I go and stick a foam board on the outside of my stud frame? Because then I can get an extra 1.5, 2, whatever thickness I want on that wall, and intuitively go, yeah, that's easy win. Let's do that. And yes, from a thermal conductance point of view, that's a good solution. The problem is that you're not considering the moisture movement through that assembly. And what risks happening is that you've moved the dew point in that wall such that the interior face of the foam becomes a condensing surface. And again, vapor hitting cold surfaces, problems. And so if you're going to do something where you've got a 90 mil frame and want to add some exterior insulation, it ideally should be vapor permeable. Because on a heating dominated climate, as you move out through your assembly, you want increasing vapor permeance, increasing vapor openness. And so if you put, say, a wood fiber or a mineral wool product on the outside, the water vapor can continue to diffuse outwards.
And what if you did EPS on a vented cavity? You wouldn't get the thermal benefit though, then, would you?
No, that's right. So you imagine, say, your EPS-based render board system. So ideally, you want to have a button behind that EPS in order to allow any water that gets past the cladding, past the EPS, to drain away. And ideally, you want to ventilate that cavity, because you want any moisture that might diffuse from the inside towards the outside to be able to escape. And the more you ventilate that cavity, the less that's a still air gap, and therefore the EPS that's sitting out in La La Land effectively is no longer contributing to the R value, to the thermal performance of that wall.
Visual only at that point.
Visual only, which is fine. You need something to attach your render to.
Correct, yes.
But don't go and then falsely claim that it's giving you some extra thermal performance of your wall.
Understood. Builders are often working from plans that don't show enough detail around insulation install, junctions, moisture management. How can we improve that relationship between design intent and site execution?
Yeah, it's a difficult one. I don't think I have a great answer to this, probably in different parts. But obviously the building designers, architects that are more experienced in doing these sorts of constructions have a set of standard details that they'll provide in their document package to the builder that they can go away with. And equally, builders who have done this a few times often won't need to be or want to be told exactly how to detail it. They know. And given that they're on the tools on site, ultimately having the engagement and in their minds understanding the 3D of how this is going to all go together, how they're going to sequence it, is absolutely critical. But you've got to get from go to woe, and that's tricky. But we do have to improve our detailing. I think it's great that some of the product suppliers now are providing standard details. So that saves all parties from having to draw their own details if they can just essentially borrow those standard details, and great from a product supplier's point of view, of course, because they have a greater deal of confidence that their product, when installed, will be installed in accordance with manufacturers' recommendations, and therefore is more likely to work effectively or as designed.
So really the only solution to making, I guess it's that what gets designed and what gets built gap, that performance gap that we're talking about here essentially. And the only way to close that is upskilling everybody.
I think so. But especially, to put the onus back on the poor builders is like,
it's not fair, is it?
It's kind of not fair, but what gets built is what matters. What gets drawn is irrelevant. What people like me model is irrelevant if it's not related to what actually happens on the ground on site. And I think this is really terrific, the way the industry, or certainly the subset of the industry in which I work, has sort of transformed in the past decade or so, is that we have some fantastic builders over where I am, at least in Victoria, that are super engaged with this, now increasingly experienced, and can deliver on this without necessarily having to have every nth detail drawn for them. And there's always this balance, isn't it? You don't want a 2-page drawing set, but you don't really want a 200-page drawing set either. And invariably, there will be details that need to be worked out on site that weren't quite worked through in the pre-construction phase.
Yeah, I was having a discussion with a builder last weekend, and he was just expressing his frustration with the level of detail that they get on the plans, and the communication and collaboration in the early stages not being there, and just having to make it up on site as they go. I can imagine that would be tricky.
I think probably the other thing there to mention too is probably the idea of earlier contractor involvement in a design and project, and given where prices are at the moment in the construction industry, the idea of going to competitive tender doesn't seem to me to be a particularly attractive way of proceeding. By instead involving a contractor or builder early on in the design stage, particularly when it comes to that sort of construction drawings, and if they can provide input, particularly on the cost side, constructability and all of that, then it feels like that creates a more collaborative, universal engagement of all parties, so that you don't get that tension when the builder has just received a set of construction-ready drawings. Here you go build that. There's not that sense of ownership involvement, whereas, of course, if the builders had the opportunity to influence the design, and they both understand it and they have that sense of ownership as well, which hopefully helps on site.
Absolutely. And I am seeing more of that happening, but it's still not happening enough. There's still a lot of attention and frustration in that translation period. But yeah, I am seeing more of it happen. So we'll focus on the good. So roof color is rather a hot topic. It's there for aesthetics, but it's also there for performance. And there's this contention between light roofs and dark roofs. Which one's better? Heat island effect, et cetera, et cetera. What are your thoughts on that?
Okay. So it depends, obviously, on the climate. It depends on the building as well. Obviously for summer heat removal, or minimise the absorption of solar radiation in the summer, you want a light colour, like, say, a surf mist type of colour. But in winter, you generally would prefer to have a dark colour in a southern Australian type of climate, from a thermal point of view. However, from a moisture point of view, you often want a dark colour year-round. And what I think matters here is not so much the colour of the cladding or the roof, as much as what you do immediately underneath it. And so in high-performance construction now, we tend to have a batten in the walls for ventilation and drainage. And I think many builders would be doing that even in conventional construction now too, absolutely rightly, for condensation management and bulk water ingress. But similarly also do the roof in exactly the same way. So the roof is just a wall turned on the side. And by creating that ventilation gap between the roof sheet and your sarking or membrane underneath, and allowing air to move through there, you allow any water that should happen to get into that roof to drain down and away. You allow any moisture that should drive up and out into that cavity to be carried by that air movement through and away. And if you have a dark roof sheet colour like I was talking to this builder this morning who's got a night sky roof, so super dark. It just creates a much stronger chimney stack effect. And we were talking about the depth of the batten required. And if you have a dark roof sheet colour, then you don't necessarily need as deep a batten, because the dark roof sheet is creating much more warmer air in that cavity and therefore driving stack ventilation, just like a chimney. And that's what you're trying to do. Just think of the building as a layer where the outside of your sarking, both a wall membrane and up onto your roof, is really effectively the outside of the building. And then I'm going to stick this sort of like almost umbrella around the building. That's this wall cladding, and my roof sheet is set off from that sarking. They're separated from it. So they provide shading and they stop the bulk water ingress to hit that sarking layer. But other than that, they're essentially a separate kettle of fish altogether. And as soon as you do that and you provide lots of ventilation in that cavity, which you desirably do or want to do for both condensation and to reduce summer overheating, then the colour of cladding becomes much less important. And so your client architect can choose whatever cladding colour that works for their aesthetic.
In Queensland, I think that anything darker than monument is not allowed under their DTS rules for overheating purposes.
And in those cooling dominated climates, that starts to conceivably make some sense. Yeah,
it becomes as you say, is a moisture control issue. I think if you had to take your pick between moisture and heat, I think you'd have to take moisture as a priority, wouldn't you?
Water kills buildings.
Yeah.
If the building's dead, doesn't matter with how energy efficient it is.
Precisely.
So you've got to deal with that first.
Yeah. Okay, a couple of questions. Windows are the trickiest part of a building envelope. So what do you think builders should know about getting the best thermal performance out of the window? Because it's not just about the component itself. The installation matters a lot as well. So what's your...
And the window system. So the window system is both glass and frame. So you've got to consider both of those. To touch on the install, a classic brick veneer install is probably the worst way you can possibly install a window, because we go and stick it out in that cavity. It's essentially out there in la la land. And if you want the best thermal performance for your building, then you've got to have all of your insulation layers in the same plane.
In alignment.
Alignment. So your wall insulation, your stud frame, and then your hits your window. The window's not sitting out there, la la la. And that this is, to digress, this is why one of the problems with skylights. If I take my wall and turn it flat and have a window, which is now called a skylight, I can't have that sitting in the thermal envelope.
Yeah, it's going to be poking up.
It's got to be poking up, the drainage. And as soon as I make it poke up, I've got a problem. Because I've got a thermal bridge all the way around the perimeter of that skylight. And so I need to get funky with some XPS, cut a collar around it, try and insulate around that skylight, which is a lot of faffing around. So you've got to ask, at what point do I really want this skylight?
How much is that light worth to me?
Exactly. And, skylights are sort of the bane of my life. But in a wall, that's exactly what you're doing with a brick veneer, traditional brick veneer install. You're putting the window out in la la land, just like a skylight. So we can't be doing that. And I think we increasingly, certainly in my universe, builders get that now, and we're over that. Where I think things get funky with windows is probably the frames, and I think we get that aluminium is terrible. Thermally broken aluminium is better. UPVC are very good. Timber is obviously very good, but come at a price premium. And then the other critical component is the glazing specification, and we seem to get that wrong a lot. We're seeing double glazing as standard, but your cheapest double glazing might have very modest gaps. They might not be argon filled, and the argon helps, but it's not doing the really heavy lifting. The really heavy lifting in a good double glazed unit is the low E coating. It's this invisible spluttering of silver and funky chemicals inside the pane of inside the glass IGU, or the insulated glazing unit, and what that's doing is changing the radiation, changing the way the emissivity of that glass surface works, and that makes a big difference. So when you say you've got double glazing, my first question is what sort? Because there's a factor of 2 difference in the thermal transmittance between rubbish double glazing and really good double glazing. And so you need to consider your building. Is it in Adelaide? Is it Melbourne? Is it Hobart? Is it in Cairns? And then look at exactly the specification of that low E coating, because it can be tailored to do different things. In cairns, you're trying to tailor it to stop solar radiation getting in always. In Melbourne or Tassie, you're trying to encourage, sort of trying to allow as much of that solar radiation to get in winter as you possibly can.
Mm-hmm.
And so the composition of that coating will change.
Mm-hmm. Mm-hmm. So that is not something a builder can control. They can't. So that specification comes out of the modelling, whether it's a NatHERS building code compliance model or whether it's a PHBP model. That's where that specification comes from. As far as install, what can the builders do?
Of the window?
Of the window, yes.
Yeah. So I suppose we touched upon the thermal performance,
Mm-hmm.
so make sure it's in the plane of the insulation.
Yep.
And the other part of the installation is probably just water management.
Mm-hmm.
So, where's a wall going to leak? The first place it's going to leak almost invariably is at the window sills. And so you've got to consider how you detail your taping
mm-hmm.
of your sarking. So your exterior membrane, which, to take a step back, what's the role of that exterior membrane? The sarking, as we used to call it. Well, first and foremost, the primary reason for that is your second line of defence for bulk water.
Mm-hmm.
And bulk water is simply a fancy term for liquid water.
Yep.
Rain. Rain. That's all it is.
Rain.
It's just rain. Yeah. So the rain, what does Joe Steinbrück always say? There's claddings that have leaked and the claddings that haven't leaked yet. Mm-hmm. Got to assume your cladding's going to leak.
Yeah.
Water's going to get in and it's going to drive onto the stud frame. And of course, when it hits timber and glass wool, you're in a world of pain. So the sarking's role is to stop that liquid water getting any further.
Mm-hmm.
But then by putting that membrane on the exterior of your stud frame, you've got to make sure it's not a condensing surface. And so you've got to make it vapor permeable, which is now what we do
mm-hmm.
in southern climates in Australia. But then you've got to make it continuous onto your window.
Mm-hmm.
And this is where you've got to tape that membrane onto the window to allow any water that gets in past the flashings to get down onto the tape, to drip down onto your weather resistive barrier or your sarking, and to drain away.
Mm-hmm. And would you say that's a more important use of product than, say, expanding foam around a window installation?
Well, I'd say the expanding foam has a different role. Mm-hmm. So the expanding foam really is about reducing the thermal bridge around mm-hmm. the rough opening. That mm-hmm. 10 mil gap that you've got around, you want to insulate that always. And that's helping somewhat with air tightness too, assuming you're using a low expansion elastic type foam, which I assume everybody is. But it's not really going to help a great deal with water management. Mm-hmm. You've really got to rely upon the tape and the sarking membrane to provide your last line of defence. Mm-hmm. Well, not necessarily the last line of defence, but your water protection.
Mm-hmm. I think a lot of builders use that expanding foam for air tightness. So that it works for that too, to an extent, right? Because it cracks and things over time.
Well, and then this comes down to its elasticity properties.
Yeah.
The elastic ones will help, but of course, if you get a hairline crack as it delaminates off the timber, then it's no longer airtight. But what I would argue is you need to tape the sarking to the frame anyway for water management.
Yeah.
And by doing that, there's your airtightness.
Yeah.
And so whatever you do with your foam beyond that is an additional win.
Mm-hmm. I think what you say about the claddings too, the claddings that have leaked or claddings that will leak, I think it's a mind shift in industry that we have to understand. We have to remember that claddings are really aesthetic only. They're not the water barrier. They are not the water barrier because they're never going to be perfect.
They're never going to be perfect, but you're hoping that they're going to deal with the vast majority of bulk water, 90+%. Mm-hmm. And certainly with your roof sheet, you're hoping they are, because if you only get a tiny percent of that water leaking past your roof, you're in a world of pain. Mm-hmm. So to be fair, no one layer is ever 100%.
Yeah.
So even your sarking, even though no matter how diligently you do it, it's not a submarine. You can't take that building and throw it in the ocean and expect it won't spring a leak, because of course it will. In as much the same way that your airtightness membrane, be that the external membrane or an internal one dedicated to the purpose, you're never getting zero ACH. You never have a perfectly airtight building. And so no one layer is 100%. Trying to do your best, your diligent best to make them so, but you need redundancy. You've got to assume that the thing's going to fail, the cladding's going to fail, you're going to get water through, the window flashing's going to fail. What happens then? The question is always, how far do you go? Because you can assume the tape will delaminate, so you need like a butyl tape on the sill as well. Then you need a back dam, you need a sill pan, and you need all sorts of things. At what point do you say, well, a meteorite might hit the building too? So,
Yeah.
You're trying to minimize risk.
Yeah.
You can never eliminate risk.
Understood. All right. So last question that I ask all of my guests is, out of everything that you've learned in your career, what is the one thing that you want the listener to know?
It's hard. We don't know. I think we've got to be really contrite and honest with ourselves. Like, sometimes I get a bit upset when we say that was doomed to fail. Well, that will absolutely succeed. I guarantee it. Well, there's no guarantees in life. And all we're trying to do is stack the deck in our favor. We're trying to do everything we diligently, prudently can within a budget, within time constraints, within practical limits that the real world is all about, to try and minimize the risk. And dare I say, beyond that, we're just hoping. Yeah. And we're constantly trying to improve and learn from our mistakes, because our building materials are constantly changing, and our techniques and the codes changing, and the way we have to do things changes. But we can't eliminate the risk. We're just seeking to minimize the risk. Mm-hmm. Mm-hmm. And we should be talking about probabilities and relative risk. I think this is less risky than that, therefore we should do that. Mm-hmm. Not that one's going to work and that one's going to fail.
Mm-hmm. Very good. Thank you, Cameron.
Thank you.
Thank you for your time. That is all for today. Thanks so much for tuning in. There'll be another episode in a fortnight, so if you would like to listen into the types of conversations that I have all the time, please subscribe on your chosen platform. Rate the show, leave a comment, whatever you like, share with your friends and family. I'd love for you to spread the word about the Building Styrology Potty. There's a link in the episode description where you can head to a landing page, and there are some show notes there with relevant links and a full transcript of the show as well, and also links to my socials. So if you're not already, I'd love for you to follow along there too, as I share lots of building science and building biology tips. There's also a contact page where you can send me an email or even a voice message. So if you've got questions or suggestions or guest ideas, I'd love to hear from you. I want to know what you want to know, so please get in touch with me. Thanks again. I'll be back in 2 weeks, so until then, happy healthy building.